Thermodynamics is a field in physics and chemistry that deals with quantifying forms of energy and the relationships between those forms. For this week, we're going to discuss a few of these quantities as they relate to the properties of gases. Pressure in gases is transmitted by the force of a huge number of gas particles colliding with a surface. The SI unit for pressure is the Pascal, and since pressure is a force applied per unit area, a Pascal is 1 Newton per meter squared. Standard air pressure at sea level is 101,325 pascals, or 101.325 kilopascals. The air pressure you're feeling right now is more or less equivalent to the mass of all the air above you accelerating towards the Earth at 9.8 meters per second squared and applied to the surface area of your skin. A can of pop is pressurized by carbon dioxide in the headspace above the liquid. We can increase the amount of carbon dioxide in the headspace by releasing some of the carbon dioxide that's dissolved inside the liquid by shaking it up. Like we will with this homemade fermented beet juice. Here goes nothing. When the amount of gas goes up, pressure goes up. This is also a demonstration of Avogadro's law, which states that more gas molecules take up more volume. The extra gas in the bottle took its extra volume as soon as it could by displacing liquid out through the neck. Volume is a quantity of three-dimensional space and has the units meters cubed. The second way we can increase pressure inside a can of pop is by heating it. We're not going to try this one at home. Temperature is a function of the energy stored by the gas, and its unit is Kelvin. 1 Kelvin has the same size increment as 1 degree Celsius, but instead of placing the 0 at the melting point of water, it's placed at negative 273.15 degrees Celsius, what's known as absolute or thermodynamic zero. Gases store most of their thermal energy as kinetic energy, translational motion, and that's proportional to its speed. The same number of gas molecules colliding faster with the wall exerts more force on the wall, and so increases the pressure. When temperature goes up, pressure goes up. This principle is known as Gay-Lussac's law. If the heated gas isn't inside a can, but is instead inside a flexible container, extra force against the walls will simply expand the walls, like in a hot air balloon. The heated air inside the balloon takes up more space than the ambient temperature air outside the balloon. A lower mass per volume means that it has a lower density than air. When temperature rises, volume rises, and the balloon rises too. This is an example of Charles's law. The final way we could increase the pressure inside the can is to make the can smaller. It's tricky to do this in practice, and even here I would say that the can bursts because the metal fails, not because the inside volume or pressure changed substantially. A better example is a piston in an internal combustion engine. The downstroke of the piston decreases the chamber volume, increasing the pressure of the air and gas vapor mixture before it combusts. As the volume goes down, the pressure goes up. This is also known as Boyle's law. Combustion then generates more gas and higher temperature, invoking both Avogadro's and Gay-Lussac's laws to further increase the pressure and drive the piston up, pushing on the rotor and delivering transformed chemical energy as power to the wheels. That's a lot of relationships to keep track of individually, but the good news is that with just one more piece we can tie them all together, and that's what we'll do in our next video.